Students, today let us concentrate on some of the problems on Fourier series representation of periodic signals. Okay, so last class I told you about the Fourier series representation of periodic signals, continuous time periodic signals, and you also saw some of the properties, important properties of Fourier series. And I also told you about the frequency spectrum of Fourier series. So frequency spectrum, you have two things. One is the magnitude spectrum, which we plot the magnitude of the Fourier series coefficient versus k, and the phase spectrum we plot the phase of the Fourier series coefficient with respect to k. Okay, so today let us see some of the examples on computing the Fourier series coefficient. Now, given any periodic signal, that is continuous time periodic signal, you have to find the Fourier series coefficient. So the given signal can be, sometimes they'll give you the signal as a function like showing you on the screen, and sometimes they'll also give you the graphical representation of the signal. So anything is given, you should be able to find out the Fourier series coefficient. Okay, so let us consider the first example. So here you are supposed to find out the Fourier series coefficient. The signal given is x of t is equal to sine omega naught into t. You need to find out the Fourier series coefficients, draw its spectrum. Now when I say draw its spectrum, you are supposed to draw its magnitude spectrum and also its phase spectrum. Okay. So now let us consider the given signal. X of t is equal to sine omega naught into t. Now sine theta, you know that it can be represented as e power j theta minus e power minus j theta divided by 2j. So we have represented that. So sine omega naught into t is e raised to j omega naught into t minus e raised to minus j omega naught into t divided by 2j. Okay, so and if I separate out the terms, I get x of t is equal to 1 over 2j into e raised to j omega naught into t minus 1 over 2j e raised to minus j omega naught into t. Now let us find out the Fourier series coefficients by comparing this equation with the synthesis equation of our Fourier series. That is, we know that x of t is equal to summation of k varying from minus infinity to plus infinity x of k into e raised to j k omega naught into t, where x of k is the Fourier series coefficient. Now this is what we have to find out for the given signal. So I can find out the Fourier series coefficient. Like I can compare the given signal x of t with this standard signal and I can find out the Fourier series coefficients. Now in our signal we have only two components. Okay, so let us expand this equation and let us check what are the two components. That is, these two are related to which Fourier series coefficient. Now when I expand this, I get like on the positive side, if I take from k is equal to 0, so it becomes x of 0 plus x of 1 into e raised to j omega naught into t plus x of 2 into e raised to j 2 omega naught into t, and so on. So the value of k changes as we as the value of k in this exponential term varies as you change the value of k. Even the same thing holds good even if you go on the negative side. Okay, but I'll expand this only for two terms. Why? Because in our expression for x of t, I have only e raised to j omega naught into t, that is supposed for k is equal to 1. And here I have e raised to minus j omega naught into t, so where k is equal to minus 1. So I'll expand this for k varying from minus 1 to plus 1. Okay, So this is the expansion what you can see here, and x of 0 term we don't have, that is equal to 0. So after expanding, if I compare, so let me call this as the given expression as 1, and whatever I have expanded for k is equal to minus 1 to plus 1, let me call this as 2. So if you compare 1 and 2, we get x of 1 is equal to 1 over 2j, and x of minus 1 is equal to minus 1 over 2j. So these two are the Fourier series coefficients, and x of 0 is 0. X of 0 is also equal to 0. So for the given problem, we are getting two Fourier series coefficients. Now what is the next thing? After finding the Fourier series coefficients, we have to plot the magnitude spectrum and the phase spectrum. Now you have to, for the first value, that is the first Fourier series coefficient, plot the magnitude and phase, and even for this you plot the magnitude and phase. Then for the spectrum, you have to plot those values versus k. Okay. Now x of 1 is 1 over 2j. So 1 over 2j can be written as what? X of 1, I can write it as 1 over 2 is 0.5. So if I take j to the numerator, so it becomes minus j. So it is minus 0.5j. Okay, so or I can say it is 0 minus 0.5j. Now you know how to compute its magnitude. In the previous class I've shown you. If you have any complex quantity like a plus jb, so how do you compute its magnitude? It is just taking root of a square plus b square. So similarly for x of 1, you have 0 minus 0.5j. So take root of 0 square plus 0.5 square. That is the magnitude. So you'll get half. And what about its phase? Phase is tan inverse of b by a. Correct? So it is tan inverse of b by a. Okay. So using this you have to find out for x of 1 what is the magnitude and what is the phase. So for x of 1 the magnitude is 1 by 2 and the phase is pi by 2, and for x of minus 1 the magnitude is 1 by 2, the phase is minus pi by 2. So that we have plotted. So this is the magnitude spectrum of magnitude versus k. So we have two Fourier series coefficients, that is 1 and minus 1. So it is minus 1 and 1. So minus 1 it is half, the magnitude is half, and the phase is pi by 2. And for k is equal to 1, the magnitude is half and the phase is minus pi by 2. Okay, so this is how we have found the Fourier series coefficients, and we have plotted the magnitude spectrum and the phase spectrum. So let us go to the next example. Okay, so here we had on the first example, we had only one function here, sine omega naught into t, one signal. Okay, but here I have sum of two signals. So you have to given what x of t is equal to sine 2 pi t plus cos 3 pi t, summation of two signals, two sinusoidal signals. You have to evaluate the Fourier series representation for the signal. That is, you have to find out the Fourier series coefficients and then sketch their magnitude and phase spectrum. Now, as you all know that the Fourier series coefficients you are finding for a continuous time periodic signal. Now, before going for computing, you check that the given signal is periodic or not. So earlier we know that sinusoidal signal is periodic. Yes, so we computed. But here we have summation of two periodic signals. This is a periodic signal. This is also a periodic signal. Now you have sum of two periodic signals, because we don't know the addition of periodic signals may be periodic or may not be periodic. You know how to check the periodicity when you have a summation of two periodic signals. So first check whether this addition of two periodic signals is periodic or not, and then you have to proceed. So how do you check whether this addition of two periodic signals is periodic or not? What we do is we compute the fundamental period of the first signal, we compute the fundamental period of the second signal, and we take the ratios of the fundamental periods. If the ratios of the fundamental periods are rational, then we can say that the given signal is periodic. If the ratio is irrational, then the given signal is not periodic. So let us find. So for the first signal sine 2 pi t, we have omega naught 1 is equal to 2 pi. You know what is omega. Omega is nothing but 2 pi by t. So for omega naught 1, I have written it as 2 pi by t1, which is equal to 2 pi. So 2 pi will get cancelled. So we have t1 is equal to 1 second. Next, for the second signal, omega naught 2 is equal to 3 pi. So what is omega naught 2? 2 pi by t. Pi will get cancelled. So you have t2 is equal to 2 by 3. Now take the ratios of t1 and t2. Yes, so you are getting a 1 divided by 2 by 3. So it is a rational quantity. So the given signal, that is x of t, which is addition of these two periodic signals, is periodic. So I can proceed for computing the Fourier series coefficient for the given signal. So now, as we did in problem, so we have expanded sine 2 pi t, so which is 1 over 2j. You have e raised pi t minus e raised to minus j 2 pi t divided by 2j. So we have separated the terms. Similarly, for cos 3 pi t also, e raised to j 3 pi t plus e raised to minus j 3 pi t divided by 2. And after that, we have separated the terms. Now, what we did in the previous case, we related this, we compared this with the standard Fourier series representation, that is the synthesis equation of Fourier series x of t, and then we found out the Fourier series coefficients. So similarly, now this x of t is going to be compared with the synthesis equation of the Fourier series representation. Now you can see from where to where shall I expand this for comparison. Now in the given expression x of t, you can see in the exponential term I have e raised to j 2 pi t, e raised to j minus 2 pi t. Here e raised to j 3 pi t, e raised to minus j 3 pi t. That means this is got for k is equal to 2, and this is got for k is equal to this is got for k is equal to minus from minus 2 to this is got for k is equal to 2 minus 2, k is equal to minus 3, and k is equal to 3. Okay, so we have to expand this for k varying from minus 3 to plus 3. We have to expand from, so I'm sorry, this is once again. So this is for k is equal to 3, for k is equal to minus 3, k is equal to 2, and k is equal to minus 2. So we'll expand this x of t for k varying from minus 3 to plus 3. But here I don't have any term which is related to x of 0. So I don't get. Okay. So after expanding, if you compare this expression with this, let me call this as equation number 1. And after expanding, I call this as equation number 2. Okay, then I get x of 2 is equal to 1 over 2j, this one. And x of minus 2 is equal to minus 1 over 2j, this one, minus 1 over 2j. Next, x of 3 is equal to 1 by 2. So this is x of 3 is equal to 1 by 2. Next, x of minus 3 is equal to 1 by 2. X of minus 3 is equal to 1 by 2. And x of 0 is equal to 0. Now we have got 4 Fourier series coefficients. So x of 0, x of k is equal to 0 for the values of k other than these two, and for k is equal to 0 also x of k is 0. Now as we did in the previous problem, for all of these Fourier series coefficients you have to find the magnitude, that is modulus of x of k, and you have to find the phase. Okay. So you can check from this Fourier series coefficients. For x of 2 and x of minus 2, I'll get both magnitude and phase because I have this j term with us. And for x of 3 and for x of minus 3, we get only the magnitude term and will not get any phase term. Okay. Phase is 0 for these two, x of 3 and x of minus 3. And for x of 2 and x of minus 2, we'll get both magnitude and phase. So I think you all know, and in the previous problem I showed you how to find out the magnitude and phase. So follow the same thing. So if you find out the magnitude of x of 2, it is 1 by 2, and magnitude of x of minus 2, it is 1 by 2, and magnitude of x of 3 is 1 by 2, and magnitude of x of minus 3 is also 1 by 2. And phase, like it is similar to the previous problem, right? You get two phases, one is plus pi by 2, the other one is minus pi by 2. So we have plotted that here. So x of minus 2 minus 1 by 2j, so it is plus pi by 2, and x of 2 is 1 over 2j, so is minus pi by 2. And for x of 3 and x of minus 3, we don't have j terms, so I don't get any phase, so the phase is 0. Okay, so this was about the second problem where you had the addition of two periodic signals and we had to find out the Fourier series coefficients of the sum signal. Okay, so before that we had to check whether it is periodic or not. So after checking, we had proceeded to find the Fourier series coefficients and then to plot the magnitude and phase vector. Now this is the next example where the graphical representation of the signal is given. Now for this, you need to find out the Fourier series coefficients, draw its magnitude and phase vector. So when you observe this signal, this resembles which signal? Can you tell me? Like if you observe this has a pattern. So it is a periodic signal. So if you observe for each duration, if you observe, this is nothing but a exponential signal. This is an exponential signal. So you know exponential signal, it is either a decaying exponential or it is a growing exponential. So if the given exponential signal is like this, it is e raised to t, which is a growing exponential. Now whatever you have here, the repetition, so that is your decaying exponential, e raised to minus t. And this pattern, that is this exponential pattern, is repeating. So the given signal is a periodic signal. Okay, so before proceeding to find out the Fourier series coefficients, okay, so let us identify its period. So you can observe that it is repeating for a fundamental period of t is equal to 1. And the periodicity condition is also satisfied by observation. So you can observe that x of t is same as x of t plus, that is x of t is equal to x of t plus 1. So it is a periodic signal. So we have found out its fundamental period, that is t is equal to 1. Let us find out the fundamental frequency omega naught, which is equal to 2 pi by t. T is 1, so I get omega naught is equal to 2 pi. Now let us proceed towards finding the Fourier series coefficient. So now I'll consider the second equation of the Fourier series representation, that is the equation for finding the Fourier series coefficient x of k. To find the first two examples, what I did was I expanded given x of t, I expanded x of t for the given problem, and I compared that x of t with the x of t, standard x of t expression, and we found out the Fourier series coefficients. Okay. In this problem, directly I am using this expression to find out the Fourier series coefficients. Okay. So we have the equation to find out the Fourier series coefficient, that is x of k is equal to 1 over t, where t is the fundamental period, integration over one period x of t into e raised to minus jk omega naught into t. So let me substitute what is x of t. What is x of t? We are finding the Fourier series coefficient for a fundamental period, that is integration for a period in one period. So what is that? We found out this signal is a decaying exponential, that is e raised to minus t. So I substitute x of t is equal to e raised to minus t. And what is our fundamental period? Our fundamental period is 1. So I'll integrate this from 0 to 1, e raised to minus j k. What was omega naught? The fundamental frequency, omega naught is equal to 2 pi. So we have substituted 2 pi here. So finally I get 1 over 1, because t is equal to 1, integral from t varying from 0 to 1, e raised to minus t, e raised to minus j k 2 pi into t. Now I'll combine these two exponential terms. So t I can take it as common. So if I take t as common, I get e raised to minus 1 plus j 2 pi k t. Now let us integrate this. So integration e power at dt. So it is e power at divided by a. Okay. So I have e power minus of 1 plus j 2 pi k t divided by 1 plus j 2 pi k. So apply the limits 0 to 1. So if you apply the limits, you will get 1 minus of e raised to minus 1 divided by 1 plus j 2 pi k. So e raised to minus 1, you have to apply the limits. So first limit is 1. So when I substitute t is equal to 1, what will happen? I get e raised to, I'll show here, when I apply the upper limit. So I'll get e, when I separate these two terms, e raised to minus 1 into e raised to minus j 2 pi k 1 minus of when I apply the lower limit, that is 0. So I get e raised to 0. Okay. Now minus e raised to 0. Now e raised to minus 1 is here. E raised to 0 is 1. And what is this? This is also equal to 1. E raised to j 2 pi k is also equal to 1. So we get 1 minus e raised to minus 1 divided by 1 plus j 2 pi k. Now we have to find out, this is the Fourier series coefficients. Okay. Now what we have to do? We have to plot its, as per your question, you have to draw its magnitude and phase spectra. So to plot its magnitude and phase spectra, I have to take its magnitude and phase. So I'll show you how to take the magnitude and phase of this x of k. Then after taking, we need to vary the values of k, and for each and every value of k, we have to find out the magnitude and phase, and after that we have to plot it. So this is how you have to. So what was x of k? 1 minus e power minus 1 divided by 1 plus j 2 pi k. So 1 minus e power minus 1 divided by 1 plus j 2 pi k. So in the denominator, we had the complex term, right? So this root of 1 square plus 2 pi k whole square, and in the numerator, I have 1 minus e power minus 1. Now, you have varied, you have to keep varying the values of k. So 0 plus or minus 1 plus or minus 2. So few values you vary. So in this equation, keep on varying the values of k. So for every value of k, to find out the magnitude of x of k. So these are the different values. So in this expression, you need to keep substituting this value of k for k is equal to 0. So k is equal to 0, I get x of 0 is equal to 1 minus e power minus 1 divided by root of 1 plus, this is 0. K is equal to 0. So this term is 0. So I get 1 minus e power minus 1 divided by 1. So that is your 0.63. Next, put k is equal to 1. So k is equal to 1. I get 1 minus e power minus 1 divided by root of 1 plus 2 pi the whole square. So that is nothing but your 0.1. Okay. So for few values of k, we'll find out all the magnitudes of the Fourier series coefficients, and after that we have plotted. So this is the magnitude spectra of the given signal x of t. Similarly, phase also. So phase is for a given complex quantity. How do you calculate the phase? Tan inverse of b by a. So here, which is b, and since it is in denominator, the complex quantity, so that's why we have taken minus tan inverse of b by a. So what is b? 2 pi k divided by 1. Yeah, 2 pi k divided by 1. Okay. So now in this, you keep on varying the values of k. So k is equal to 0, and whatever k values you took to find out the magnitude, for the same k values you find out the phase. Okay. And after finding all the values of phase, you have to plot the phase of x of k versus this k value. Now, when you observe the plot, I wanted to tell you one thing. So, when I told you about the magnitude and phase spectra, I told that the magnitude spectra is even function. Okay, so you can see that x of k is same as your, this is your x of k, right? So, this x of k is same as your x of minus k. So, this is an even function. And when you observe the phase spectra, you can see that x of k is equal to minus of x of minus k. So we have, this is a odd function. So from the plot you can observe that whatever we understood, it is correct. Magnitude spectrum is a even function and phase spectrum is a odd function. So let us continue. So this is an other problem where once again the graphical representation of the given signal is provided to you. So you need to find out the Fourier series coefficient for the given signal. So first thing, to identify whether the given signal is periodic signal. Yes. So you can observe from the signal that it is a periodic signal. If it is periodic, you need to find out what is the period of repetition. That is, what is its fundamental period. And already in the data it's given that the given signal is a sinusoidal signal, sin pi t, and it is defined only for half of the period. For the other half it is 0. So you can, from this graphical representation, you can see that the signal is defined only for half of the period and the other half it is 0. Okay, this is 0 here and this forms the period. So you can see the same pattern repeats from here to here also. So from this, can you find out what is the fundamental period? Yes, the fundamental period is T is equal to 2. And you can also verify that the periodicity property is satisfied. That is, x of t is equal to x of t plus 5. Yeah. So let us, now we have understood that the given signal is a periodic signal and we have identified what is its fundamental period and we know what signal it is. It is a sinusoidal signal which is defined as sin pi t. So further, let us continue in finding its Fourier series coefficients. Okay. So this is the equation, Fourier series coefficient equation to find the Fourier series. So we have x of k is equal to 1 over t integral over a period x of t e raised to minus j k omega naught into t. Yes, you need to find out omega naught also. That is the fundamental frequency. Like same as the previous problem. Omega naught is equal to 2 pi t. What is the t value we found out? We found out t is equal to 2. So 2 pi by 2. 2 and 2 will get cancelled. So you have pi dt. So let us substitute this t value and omega value in this equation and also the x of t value. So we have 1 over t integral from 0 to 1. So why it is from 0 to 1? Actually, I have to consider from 0 to 2. But in this equation, I have just taken 0 to 1 because from 1 to 2, it is not defined. So no need. Anyhow, you are going to substitute it as 0. So start taken here. 0 to 1 sin pi t into e raised to minus jk omega naught into t. Now, how will I integrate this? It's very simple. If I consider sin pi t in the exponential form. So sin theta is e raised to j theta plus e raised to minus j theta divided by 2j. So in place of theta, I have pi t here. So even if I replace sin pi t in the exponential form, so for us the computation will be simpler. So we have replaced sin pi t as e raised to j pi t minus e raised to minus j pi t divided by 2j and this is multiplied with this exponential term and you can see in the next step I have skipped this step. You can say after substituting this 2j is taken outside, so that's how it becomes 1 over 4j. Okay, then you have two exponential terms, right? This is that. So what is happening here is e raised to j pi t is multiplied with e raised to minus j k omega naught into t. That is one term minus e raised to minus j pi t into e raised to minus j k omega naught into t. So you get two terms. So in this, if you take pi t, j pi t as common, if I want to show that here, e raised to j pi t into one term I'll show here. So e raised to minus j k omega naught into t. So what have we done here? We have taken j pi t as common. So j pi t as common. So if you take j pi t as common, here we have 1. J omega naught is substituted as pi. So j pi t. So I get e raised to j pi t. If I take it as common, I get 1 minus k. Or if I take minus 1 outside, then it will be 1 plus k. So this is for the first term I have shown. Similarly, you can simplify the second term also. I think it is clear now. So we have got two terms now. E raised to integral from 0 to 1 e raised to j 1 minus k pi t dt minus 0 to 1 e raised to minus j 1 plus k pi t dt. Now you integrate this and apply the limits. Yes. So after integration, in the denominator I get j 1 minus k pi. Even here I get j 1 plus k pi. Apply the limits from 0 to 1. Yes. So after applying the limits, so we have got upper limit e raised to j 1 minus k pi, because t is 1, minus e raised to 0. So e raised to 0 is 1, you know, it is 1, and this is also 1. So this one is substituted here, and this 1. And why this is being simplified as minus 1 raised to k plus 1? See, when you expand this, I'll show here. So e raised to j 1 minus k into pi is there. Fine. So this can be written as e raised to j pi into e raised to minus j k pi. So these are the two terms. So you know that e raised to j pi is minus 1. Fine. So this is minus 1 into, this is e raised to minus j k pi. This is nothing but minus 1 raised to k. Because we get, if you vary the values of k, alternate values you will get. So that is e raised to j pi, e raised to, if k is equal to 1, it is e raised to minus j pi. If k is equal to 2, e raised to minus j 2 pi. So you can keep varying the values of k. In general, so I can write e raised to minus j k pi as minus 1 raised to k. So if you combine these two, this becomes minus 1 raised to k plus 1. So that's how I get here minus 1 raised to k plus 1 in place of this minus 1. Similarly here, even this term, you simplify, you get minus 1 raised to k plus 1 minus. Okay. Now after this, so these two LCM is taken. Okay. So LCM is taken and simplified. So after simplification, see in the denominator I have j and j. So and this j. So everything after taking the LCM and simplification, these j terms will get cancelled. So I have minus 1 by 4 pi minus 1 raised to k plus 1 minus 1. And these two, if I take and simplify, okay, so I get the j term is getting cancelled. So I have 2 by 1 minus k square. And further, if I want to remove this negative sign, so I can take minus outside from this factor. So minus sign will get cancelled. So I am left out with 1 by 4 pi 1 minus, this is minus 1 raised to k plus 1 into 2 by 1 minus k square. So this is the expression for the Fourier series coefficient. Okay. Now you can further, so as the question was to find out the Fourier series coefficients for the given signal, yes, we have found out the Fourier series coefficient. Further, if you want, you can plot the magnitude spectrum. You can find out the magnitude of x of k by varying the different values of k, and you can plot the magnitude spectrum. Also, you can plot the phase spectrum for different values of Before going to this, let me complete the other part, which is also the graphical representation. Yes. So here we have find the Fourier series coefficients of the periodic signal x of t shown in the figure. So this is a periodic signal, and for this you have to find out the Fourier series coefficients x of k. So I'll be using the same expression to find out the Fourier series coefficient, that is x of k is equal to 1 over t integral over one period x of t into e raised to minus j k omega naught into t dt. Now for this I should identify what is the fundamental period of this signal and what is the fundamental frequency. So when you observe this signal, so you can see that the what is the repetition period, that is what is the fundamental period of this signal. Is the pattern is you have 1, 2 zeros, minus 1 and 2 zeros. So this is the pattern. The same thing continuously. 1, 2 zeros, minus 1 and zeros. Okay, so this is the pattern which is repeating. So the fundamental period of this signal, that is the repetition period, is t is equal to 6. Fine. So t is equal to 6. And for this, what is the fundamental frequency? We have found out here. T is equal to 6. Omega naught is equal to 2 pi by t. So substitute 2 pi by 6 here. 2 ones are 2 threes are. So you have omega naught is equal to 500. So we have substituted in this equation. So 1 over 6 integration from. Okay. So for simplicity, instead of integrating from minus 2 to, we have identified that fundamental period is 6. But instead of integrating from minus 2 to 4, we have integrated from minus 3 to 3. Both are same. See here, this is also correct. Okay. So integrating from, you can integrate from minus 2 to 4 also. Even that is correct. Just for simplification, we have considered from minus 3 to 3. So that is also correct. So from minus 3 to 3, x of t e raised to minus j k omega naught is 2 pi 2 pi by 6 we simplify. So for pi by 3 into t dt. And here you can see the signal is not defined for the entire period. It is defined only for only from minus 2 to 1 and from 1 to 2. Otherwise it is 0, right? So as per that we have separated separated the terms. So from minus 3 to 3 it is separated as minus 2 to minus 1, because from minus 2 to minus 1 it is 1, and once again from 1 to 2 it is 1. So from 1 to 2 it is 1. So we get from minus 2 to minus 1 e raised to minus j is that substituted. I have not written anything for x of t here because we know that x of t is equal to 1. So 1 into e raised to minus jk pi by 3t is same as this. Even here, okay, is same. And why we have taken negative sign? Because x of t is equal to minus 1. Okay, it is minus 1. So I have taken minus. So 1 to 2 and this exponential term. So after this, you integrate this exponential term, apply the limits from minus 2 to 1 and from 1 to 2. So after applying the limits, if you simplify, so this, if you apply the limits, so this will be a cosine term, and this is also a cosine term divided by jk pi by. So this is about the Fourier series coefficient for the given signal. So as per the given problem, you need to find out the Fourier series coefficients of the periodic signal. I think it's clear how to find out the Fourier series coefficient. Now if You also have a question like find out to plot the magnitude and phase spectra. So you can further proceed. Right, for different values of k, you find out what is the magnitude of x of k and what is the phase of x of k for different values of k, and you can plot the magnitude and phase spectra. So after this finding the Fourier series coefficients of these signals where the signal is represented in a graphical form. Now I'll go to the previous problem. So this is x of t is equal to minus t. So read the question. It says find the Fourier series coefficients for the periodic signal x of t with period 2 given by. So the signal is given, and the problem, it says that the signal is periodic with period 2, and the signal is also defined for one period. So I guess you can see t is varying from -1 to +1. Okay, it's very simple. See, from the graphical representation, you have to observe the signal, find out its fundamental period, then find out its fundamental frequency, substitute, and then find out the Fourier series coefficients. But in this problem, everything is mentioned in the problem. The fundamental period is given, okay, and for which period it is the signal is defined. It is also given from -1 to +1. So you need to just find out what is the fundamental frequency and calculate and compute the Fourier series coefficient. Yes. So consider this x of k. So x of k is equal to 1 over t integral over the period t x of t into e raised to minus j k omega naught into t dt. Substitute the value of t here. E is 2 x of t. What is x of t given to us? E raised to minus t, e raised to minus j k omega naught. What is omega naught? 2 pi by t. T is 2. So 2 and 2 will get cancelled. Pi t. Fine. So now combine these two exponential terms. So I can take t as common. So if I take t as common, I get e raised to minus 1 plus j k pi. Integrate and apply the limits. So 1 over 2, this is integrated, apply the limits. After applying the limits, this is what you get. E raised to minus 1 plus j k pi t is 1. Yes. And here this minus sign will go because t is minus 1. E raised to 1 plus j k pi divided by, already 2 is there, we have taken this term out, so 2 into 1 plus j k pi. This simplification already I showed you in the previous problem. So you can separate the terms. E raised to minus 1, e raised to j k pi. E raised to minus 1 is kept as it is, and what is this? E raised to j k pi, it is minus 1 raised to k. Okay. Similarly here, e raised to 1 is kept as it is. What is this? E raised to j k pi minus 1 raised to k. So minus 1 raised to k is taken as common. So you have e raised to 1 minus e raised to minus 1 divided by 2 into 1 plus j k pi. So this is the Fourier series coefficient computed for the given signal x of t, which is equal to e raised to minus t with the fundamental period t is equal to. So further you can continue. So as per the given question, further if you want to plot the magnitude and phase spectrum, you can continue. So this was about the some of the examples on the Fourier series coefficients.